Welcome to this Math Divulged seminar. So unlike some of the previous classes, I'm actually going to be teaching in front of a physical whiteboard instead of just like sharing the screen and writing on the screen or whatever. First of all, can you all hear me? Just message me if you can hear me. Okay, good. You can definitely hear me. Okay, thank you. So I'll be teaching today's seminar about basic linear algebra. And so if you have questions, since I'm teaching, it's probably like I'm not the one you want to ask your questions to, because then like either I would have to stop teaching to come like answer everyone's questions individually, or I would just keep teaching and not answer your questions. So that's not good. So instead you should PM your questions on the chat to Benjamin Wright, our TA for today.
Hello, everyone. Just direct all messages to me. I'm here to help.
Yes. So, okay. So, okay, let's, yeah, it's 3:06. It seems like about good time to get started. And of course, just as the standard preamble, you know, this is Math Divulged. It's a series of free classes and math things. You can find out lots of information about us at our website, mathdivulged.com. And I'm Luke Robitaille. If you're wondering who I am, you can read my bio on the website or whatever. So, but yeah, we're Math Divulged. So the title of today's seminar is Basic Linear Algebra. So yeah, so let's jump right in. So oftentimes in school, you encounter some systems of linear equations, and they tell you solve the system of linear equations, whatever. And what's important isn't the specific system so much that it is a system of linear equations. So just as an example, for example, you could have this system of equations. 2a plus 4b is 2, 4a plus 7b is 5. And you've probably encountered a lot of systems of linear equations in your life at school, whatever. And so, not all systems of linear equations are created equal. Some of them have solutions. For example, this has a solution. You can just take a is 3 and b is -1. But other systems don't. If I change it to 8b instead of 7, that seems like a small difference, but now there's no solution. Because if there were a solution, I could take this equation and then subtract twice this equation, and then I would just get 0 equals 1 if there were any solution. So there are no solutions, because otherwise you would end up with that, and you don't want that. You do not want to have 0 equals 1. If you have 0 equals 1, something has gone terribly wrong. So, what's going on? How can we better understand these systems of linear equations? And not just of 2 variables, but maybe if we had, more variables. So this is sort of some motivation for what we're about to do. And what I'm about to tell you about might seem totally disconnected from anything you might care about, but I'll show you how it has applications to these systems of linear equations, maybe has applications, like also isn't the right word exactly, but is related, and how it can be interesting in its own right. And it turns out to be very useful, but I'm in like real life to like Google or Netflix or something like that. But you know, I'm not going to get too much into that today, but basically it's definitely, linear algebra is, you know, important. But so let me get into it, and you know, it might seem like, why am I doing this? But just trust me. So, I'm going to talk about some important things called vector spaces. So I'm not going to formally define what a vector space is yet. I will do that later, but for now, just to get some intuition, basically a vector space is a non-empty set of some things called vectors. And the important part is you can add and subtract vectors, and you can multiply a vector by a real number. Like any vector, you can multiply it by any real number. And basically, it has to follow some rules that basically just say, like, the standard rules of algebra apply. And if you do that, you have a vector space. And so let me give you, so this all seems very abstract. So let me give you an example of a vector space. So a very fundamental example would be R squared, the set of all ordered pairs of real numbers. And so yeah, and normally you would write an ordered pair as like x comma y, but we want to sort of emphasize that it's a vector or something like that. So we're going to use this weird notation that would be like x, y. So it's a vector. And this is a column vector. You could have, you know, a vector like this where it's all in the same row, and this would be a row vector. But for today, I'm going to write them as all in the same column, and it's a column vector. I know, such evocative names. So anyway, so when we have these column vectors, well, I can't just say, oh, yep, it's a vector space. I have to actually tell you what it means to add two vectors and what it means to multiply by a vector by a real number. And there's a little more I have to tell you, but I'll just gloss over that for now, and I'll get to that later. But but what's important is I tell you how to add vectors and how to multiply by a vector by a real number. And that's what it takes to like have a vector space. A vector space isn't just the set, it's the set equipped with the operation of adding and the operation of multiplying by a real number. And in this case, the definitions of what it means to do these things are, you know, fairly simple. If I have a vector a1, a2 for numbers a1, a2, and another vector b1, b2, and these are just, you know, subscripts, notational conveniences. They don't mean that this is 1 and this is 2 or something. They're just arbitrary numbers. Then their sum is just add it term by term. a1 plus b1, a2 plus b2. So for example, if I have, you know, 6, 8, and I add and 1, negative 5, then I just add component by component. 6 plus 1 gives me the first component is 7, 8 plus negative 5, 3. And then to multiply by a real number, say I have a real number, lowercase r, times a1, a2, well, you can maybe guess as sort of what might be a nice way of doing this. You just multiply component by component. So for example, 3 times the vector 2, 4 will give you the vector 6, 12. 3 times 2, 3 times 4. And this makes R2 into a vector space. Yay. And so, you know, there are a lot of nice things about vector spaces. So first of all, just to give you some idea of what's going on here, that thing I told you about linear equations earlier, you can think of it in terms of vectors. So if I have, you know, 2a plus 4b equals 2 and 4a plus 7b equals 5, if I want to have, to have a and b satisfying this, it's the same as having these two vectors be equal, because, you know, two ordered pairs are equal if and only if they're equal component by component. And now I can look at this as being this vector plus that vector. Which is this times that. And so the equation just becomes, that. And so, you know, you can write it in terms of vectors. And this might seem like just algebraic mumbo jumbo, and maybe it kind of is, but this expression on the left-hand side is a good example of a general type of expression called a linear combination. And basically you have some vectors, and then you multiply each vector by a number, and you sum them all up. And I'll talk about linear combinations more later. But like, that's sort of the idea. It's sort of linear in each component, sort of. But it's a linear combination, and I'll tell you more about that later. And also you can think of it as like, I could have done this with any system of equations, system of linear equations in any number of variables. So this is sort of general in a way. And so another nice thing about these vectors is that you can sort of think of them as geometry. So if I have the plane, then I can, you know, establish a correspondence between the plane and vectors in an obvious way. Just sort of, and how I'm going to write a vector, a vector xy is a line segment that sort of goes x units to the right and y units up. Like, it has a direction. So the vector 2, 4, I can draw it starting at the origin, would go from the origin to the point 2, 4. And this is the vector 2, 4. And similarly, the vector 4, 7 will start at the origin and go to the point 4, 7. And this is the vector 4, 7. This geometric interpretation has nice properties because, and these are just examples, you know, because now adding vectors moves from a matter of algebra to a matter of geometry. If I have a vector v, which I'll write with a little arrow on top to denote that it's a vector, and a vector w, assuming, like, just drawing them as starting at the origin, basically what I do to add them is just pick up, you can almost think of it as like, pick up this line segment, don't change the direction, don't way it's pointing, just carry it without rotating it at all or flipping it or anything. Just carry it over so that its tail, it's I guess, I would say that this is the tail and this is the head or whatever. But like, so that its end without the arrow corresponds to the end of the other vector with the arrow. And it's another copy of that same vector. So then to add them, you just go from one end of the one vector to the other end of the other, like that. And so it becomes a matter of geometry instead of a matter of algebra, though we won't get into that too much today. And you can think of multiplying by a real number as a matter of geometry also. If I have, v, a vector called v, then I can think of multiplying by a number as just scaling. So this would be 2v, same direction, same way it's pointing, but just twice as long. Or this might be, square root of 2v, about 1.4 times as long. And you can even multiply by a negative number. So maybe I multiply by -3, in which case I would get -3 times v, which is same direction, but pointing the other way and 3 times as long. And I could even multiply by 0. A rather sad little vector. Just a point, basically. And so that's sort of how you can think of it as geometry. And this, these vectors have applications in physics. If you do physics, you're going to hear a lot about vectors. And in fact, if you want to hear more about physics later on in the semester, we have another seminar talking about applications to physics. So you're in luck, but that's not for today. So let's look at another example of a vector space. So let's look at another example of a vector space, because when I had R squared, the set of all ordered pairs of real numbers, why should I stop at squared? Let's make it R to the k, where k is a non-negative integer. This is the set of all k tuples of real numbers, all ordered k tuples. So, if I had k equals 3, this would be the set of all ordered triples of real numbers. If I had k is 5, it would be the set of all ordered quintuples. If I had k is 100, it would be the set of all ordered hundredtuples of real numbers. And again, I'm going to write it as a column vector rather than just writing it in a row. I'll write it as a column vector. So an arbitrary element would look like a1, a2 dots ak. And you add just like you were doing it in R squared. So you just add component by component. And the multiplication is, just the same as over here. And again, if you have any questions, please direct them to Ben, not me. Thank you. And the multiplication is just the same thing. So, if maybe I had, as an example, if k is 4, then, the vector, 1, 2, 3, 4, plus, 1, 4, 9, 16, for example, just as an, it's the vector 2, 6, 12, 20. And, if I wanted to multiply, this vector by 3, you can work out for yourself what that would be. It's not complicated. It's just, you can see, try to think for yourself, and then it's just, 3, 6, 9, 12. And so I can do this for any non-negative integer k. of course, if k is 0, then you just have sort of the set of ordered 0 tuples, which just sort of has one element, like the empty tuple. It's just sort of a very sad like column vector with no components at all. And it just has one element. And like when you add it to itself, you get itself. And when you multiply by anything, you get itself. But so that's not, so r to the 0 is not very interesting. But you have this r to the k. And then as before, you can think of this as space, as geometry, except instead of 2-dimensional space, now it's k-dimensional space, which is not very easy to draw when k is large. So, but you can imagine, 3-dimensional space, if I have, I'll just sort of, to give you a real demo, suppose I have like a blue vector like this, and a red vector, or a red vector like that. So then to add them, I just take the end of the end of the blue marker to the tip of the red one, maintaining the same direction. And then their sum just goes from the end of the red one to the tip of the blue one. Just sort of as a demo of what adding them could be in, say, r to the 3, since we live in 3 dimensions. And I want to particularly draw your attention to the fact that this r to the k, in a geometric sense, lives in a space of k dimensions. So I want to emphasize, geometrically, bad marker. Geometrically, r to the k has dimension k. And I'll put it in quotes because we're not really defining what we mean or how we would do it for how we would define dimension for a more general vector space. But you can sort of see that it makes intuitive sense when I say geometrically it has dimension k. And I want to emphasize this because later on, I'll give you a definition of the dimension of a vector space, at least, a finite dimensional one. And I'll talk about dimension as it applies to vector spaces, and how it you can define the dimension in sort of an algebraic way, as opposed to having to do geometry. And it's going to work out that sort of our algebraic notion of dimension and our geometric notion of dimension are going to line up quite nicely. But let me give you one other example of a vector space. This is a pretty funny one. You could take as a vector space, I'll call the set S. Clearly it's non-empty. The set of all functions f from R to R. And this, it's not really clear how you would want to represent this with geometry. I mean, sure, you can draw an individual function with geometry. If I want f of x is x squared, I would just do, a parabola, whatever. But to draw the set of all functions, that would be kind of a tall order. And it's going to turn out that we're going to think of this vector space as being infinite dimensional. But I mean, to tell you it's a vector space, I'd have to tell you how to add and multiply by a scalar. And it turns out just if I have functions f and g, I can define a function f of g, f plus g. So just like f plus g of x is f of x plus g of x for any x. And if I have, a function f and a number r, little r, I can define rf as rf of x is just, r times f of x. And so it works out to be a vector space. And so, the point is there are a lot of vector spaces. And most of the time in real life, and definitely most of the time for today's talk, we'll primarily be concerned with finite dimensional vector spaces. And I haven't defined what that means yet, but like, I'll talk more about what that means later, but like this one is just really big. And so finite dimensional ones are more tractable, but I'll tell you more about that later. But enough with these examples. I want to actually give you the definition of a vector space. This will look kind of technical, but this is quite important. And having these sort of technical definitions with lots of axioms is sort of foreshadowing to the talk we have next week about basic abstract algebra, which I hope you'll all come to, which is also taught by me. That's the plan. But it's sort of important to have these, to grasp these, these statements with lots of axioms. So, definition. Shun, not definiton. Definition. A vector space V over R, and it is possible to have a vector space over some other number system. And that's sometimes useful, and to do that, it would constitute the multiplication of being like multiply by a number from the other number system instead of by the real number. And these are, these exist in mathematics, and sometimes they're your friends. But for today, most of the vector spaces are over R. So I'm just going to be lazy and abbreviate vector space over R as just vector space. But I'll tell you a bit more about vectors. I'll mention that about vector spaces over other number systems a bit more later. So basically, a vector space V over R is a set V of things called vectors. And we want it to be non-empty, but it'll turn, the empty set would be a very boring vector space. How could you imagine a more boring one? Like there's nothing there. But it'll turn out that the axioms will force it to be non-empty. There's a set V of things called vectors. So that, and I'm going to continue this list. I'm going to give you a list of properties that have to hold. And these are, and I'm going to continue it up here because this is going to be a pretty long list. But it's like nothing that surprising. It basically just tells you that like algebra works. Nothing earth-shattering. But like what's important is like we have these, and these statements that sort of are the definition of a vector space. We'll call them the axioms for a vector space. The fundamental properties that any vector space has by definition. So, okay, first off, there's this addition operation. So I should actually say, it's not just the set, it's together with addition, a function from V to V. I mean, a function from the set of ordered pairs of things from V to V, and scalar multiplication. That's S-C-A-L-A-R. And this is just a fancy word. In this context, the word scalar just means a number. And when we say scalar, we're sort of emphasizing that we're dealing with a number as opposed to a vector. So in physics, to give you, because you'll hear this in physics, like there are some things that are vector quantities and some things that are scalar quantities, and basically like the vector quantities have a direction, but the scalar quantities don't. So like in physics, and it's okay if you don't know physics, you don't need to know physics for today's talk, but like, just as an example for those of you who do know physics, velocity incorporates your speed and your direction. So it's a vector quantity, but speed is just a number. So it's a scalar quantity. And so that's sort of another example of this word scalar. So basically, scalar multiplication, which basically takes an ordered pair of a number and a vector and returns a vector. So that the first property, Roman numeral 1, addition is commutative. So if I have a vector A and a vector B, their sum is the same either way. Addition is associative. And let me make sure you can see that. Okay, good. Let me move over to the other board. So there is a vector 0, the 0 vector, so that and we want these to hold in general, so that for any vector A plus 0 is A, and it's also equal to 0 plus A. So, you know, again, this is what if you have something called 0, this is how you expect it to act. You expect to have that 0 plus anything is 0. And then the next axiom is basically telling us that we can subtract, but it's not actually about, like, we don't actually have to say subtraction. The important thing is to have negatives. So for any vector A, there's a vector negative A. So that basically A plus negative A is 0 in either order. But of course, we already said addition is commutative, so I don't really have to say in either order. The 0 vector, which is not the same as the number 0, but okay. And some books will tell you that you have to have as an axiom that, like, the product of a number and a vector is actually in V, but that's sort of implied. It's sort of an unwritten rule. But, like, it is important that the product of a number and a vector actually be a vector in V. So you do need that, but I'm not going to write it down because it's sort of implied. And so you need to have that let me check over. Oh yeah, and some books will tell you that you need an like the book I'm looking at off to the side mentions, like, in that book, the first axiom, I think, is, like, in that book, one of the axioms is that the sum of two vectors in V is actually in V. But again, I'm just considering that sort of an unspoken rule. You do need that, but I'm not going to explicitly write it down. So then you have some other axioms that basically are, again, just algebra. For any real numbers, x and y, and any vector A, x plus y times the vector A is x times A plus y times A. These two plus signs have different meanings. This is just the standard addition in the real numbers. This is addition in the vector space, the sort of addition in quotes. So just sort of be a little careful. And this tells you that you have the distributive property like this also. For any real number x, x times A plus B is x times A plus x times B. And then you have the axiom that for any numbers x and y, xy times A is x times y times A. And this multiplication is different from that one. this is multiplication in the reals, while this is our scalar multiplication in quotes. And then finally, the last axiom, which I guess is, no, just VIII, okay, is that 1, the number 1, times any vector is that vector. Okay. So, you know, so that's the whole list. You made it through. You survived the whole list. And so this is the definition of a vector space. And this looks really abstract, but just I don't have that much board space. I'll just start erasing here. So example, now instead of just waving our hands and saying, yeah, sure, it's a vector space, whatever, we can by the way, just quick interruption. We have another person to answer your questions now. So you can send your questions to Ben or to Brian Liu, the other co-host now. So this way we can help everyone to have answers to questions instead of just, you know, having too many questions for one person to reasonably answer. That can be better for 2 people. So send your questions to pick one, and, you know, I don't know, flip a coin, and if it comes up heads, send it to Ben, and if it comes up tails, send it to Brian, or something like that. It doesn't really matter. Just, you know, split your questions among the 2 of them or something. So anyway, back to what I was saying. So an example, R squared really is a vector space. We can actually like prove it instead of just saying, yeah, sure, it's a vector space. It looks like a vector space, whatever. So I'm not actually going to go over and check because like, it's not really very enlightening. Like, you have to check that the sum of 2 vectors really is in R squared and the product really is in R squared, like the scalar multiplication. And then you basically just have to check all this, but like, these turn out to be really easy to check. It basically just like all the algebraic properties of this vector space will just follow identically from the algebra of R. Like the fact that vector addition is commutative will just follow immediately from the fact that just regular old addition is commutative, and similarly. So like, you should do this at some point in your life, but like, if you take linear algebra in college, you know, maybe you'll have to do this as a homework problem, or maybe it'll be in the textbook, but like, it's not the most important thing for today. So just take my word for it that you could do this in principle. One thing I should explicitly mention is the 0 vector is all zeros. And to take the negative of a vector, you just make each component negative. And so, and more generally, you can prove along the same lines, R to the K really is a vector space. And then, you know, the 0 vector would be just all zeros. And you can prove that that function, the set of functions from R to R is a vector space, etc. So, but let me tell you some of the interesting things that happen with these vector spaces. So one important concept is, so one thing I should point out, that's obvious. It will turn out, we didn't write it down as an axiom because we didn't need to, but like 0 times any vector is the 0 vector. And it turns out you can prove this from the axioms, which I'll leave as an exercise to the reader. And so let's consider what happens in a general vector space. So definition, given vectors, some vectors v1 through vn, where I should write the little arrows over them, I guess, where n is a non-negative integer. And then you have a linear combination would be of them. Would be just like for any real numbers, R1, Rn would be this vector, R1 times V1 plus R2 times V2 and so on up to Rn times Vn. So in particular, in that example I gave you a while ago of like, you know, this, so for example, for any A and B and R, this is a linear combination of the vector 2, 4 and the vector 4, 7. So now we sort of boiled down our question of like whether this, you know, system of equations has a solution, or whether any system of equations has a solution. Because you could imagine doing the same procedure we did to turn, you know, this system of equations into a system of equations about vectors, into an equation about vectors for any system of equations. So we can turn our question about linear equations into a question about vectors. Given a set of vectors, when is a certain other vector a linear combination of them? And so, and like these are vectors in R to the k for some k, where k is like the number of equations. I'm not going to directly answer this today, but like, you know, you can solve linear equations, but that's not the main point of today. The point is that this is like relevant to that. But this is sort of a motivation for doing more generally, doing things more generally. And so this sort of motivates, given vectors, look at all linear combinations of them. So another definition, given vectors v1, v2 through vn in some vector space V, the subspace, and I'm sort of cheating with the terminology, the subspace generated by them or the subspace they span, the subspace spanned. And again, I'm cheating here. The word subspace and the word span are like actual words that I'm going to define, but like it'll all line up. It'll turn out. So it'll all work out. Or the subspace that they span is just the set of all vectors. And since it's already 3:48, I think it's pretty clear that like today's lecture is going over time. So, you know, just, it's okay if you have to leave because this is being recorded. So you can watch the recording later. And you can read the handout at some point in the future, I guess, too. But, you know, if you can stay, that's nice too. because then you can ask questions in real time, whatever. It's basically the set of all linear combinations of v1 through vn. Equivalently, I can write it as like the set of anything that's r1 v1 plus dot 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 plus rn vn for any r1 through rn in r, any real numbers. So like the set of all things of this form for some r1 through rn in r. Now that I've sort of told you what this is, I should sort of back up and tell you what the word subspace means. And, you know, if you're a Star Trek fan, maybe this conjures up images of, you know, when they say subspace, they mean, you know, a hypothetical parallel universe that they use to communicate faster than light. This is nothing like that. Basically, given a vector space, a vector space of V, a subspace of V is a vector space is a subset V prime of V, so that V prime is itself a vector space under the operations of V. And so it turns out that this actually is a subspace of the vector space as a whole, because like you can just see that the sum of two linear combinations is itself a linear combination. And when you multiply this by any real number, it will turn out to itself be a linear combination. For example, you know, this. And I imagine this part seems like it has a lot of boring definitions, but it gets interesting. There are more interesting things, and you know, don't worry, just, you know, keep calm and carry on or whatever. You can, for example, and you can see that the sum of two linear combinations would be a linear combination. So it, you know, it satisfies all the other axioms. Mostly you don't have to check all the axioms because they just follow from the axioms of V. Like I don't have to check that multiplication is commutative in this subspace because I already know it's commutative for all of V, for example, and you can do that for a lot of the axioms. But yeah, so it turns out this really is a subspace. Now I should tell you what the word span means. Basically, if this subspace turns out to be the whole vector space, then we say that V1 through Vn span V. That's the whole, so if it's the whole thing, then the vectors span V. And so you can see why, and you can see that they span this thing, like just, you know, take V1 through Vn as elements of this, and then they just make the whole thing by just the definition. So we're okay calling it the subspace spanned by them. So, but this is the definition of span. And so this idea of spanning a vector space is important. So another important thing is, when is a linear combination 0? When does it equal the 0 vector? So given any vectors, also I should say, when I said a non-negative integer for a linear combination, like if it was 0, then you just don't have any vectors at all. And so you just have the empty sum, which is just 0. So like, if you have a very stupid vector space that's just the 0 vector, then it is spanned by the empty set. Just if you're wondering. So yeah, there's that. So, but the question is, when is a linear combination 0? So given some vectors, there's an obvious way to make a linear combination 0, which is just make all the coefficients 0. 0 times anything gives you the 0 vector, a bunch of copies of the 0 vector sum up to give you the 0 vector. So that's obvious. So the question becomes, is it the only way to make it the 0 vector? Or can I choose some constants that are not all 0 so that this sum gives me the 0 vector? And this will turn out to be an important concept. And so we give this a name. So basically, these vectors are linearly independent if having some constants to make the linear combination 0 implies that all of them are 0, the number 0. Otherwise, there's some linear combination where the coefficients are not all 0, so at least one of them is non-zero. There might still be some of the coefficients that are 0. The point is that they're not all 0. And so at least one of the there's some way of doing this where at least one of the coefficients is non-zero. So it's not linearly independent. So you can probably guess what the opposite of linearly independent is. It is, drum roll, linearly dependent. No big surprise. And this is sort of an if and only if, but this is a definition, so I don't really need to say that. So here's a very important concept. The concept of a basis. So definition. If V1, if I have this set, and I'll sort of abuse notation, like a finite set of vectors spans the vector space if and only if like the vectors themselves span it. And similarly for like linearly independent or dependent. That's just sort of pedantic. That's a little bit pedantic. Don't worry about it. If these vectors, or actually I'll just remove the braces. If these vectors span as elements of some vector space, span V and are linearly independent, then V1 Vn is a basis of V. And this number n, the number of vectors, is the dimension of V. Now let's tread carefully here. Let's tread carefully here. I just defined this specific set of vectors and then used it to define a general property of just V. I didn't define all the vectors. So you might be wondering, whoa, maybe there's this vector space and there's this one basis over here that has 59 elements, but this other basis has only 58. Then what are you going to do? Is 59 and 58, are those both going to be the dimension of V? It turns out, and this is sort of what I was telling you, that this is actually interesting. Fact, or I should state it as a theorem. If these are both I'll say W1 through Wm are bases. The plural of basis is bases. And I know it's confusing because the plural of base is spelled exactly the same way, but in this case, it's the plural of basis is bases. Then n equals m. I do not intend to prove this today, but like, this is a statement that requires proof, but I am not going to prove it to you today. And so this is how we have this fact about the dimension. Now, all this abstract stuff might have confused you. So let me give you an example. If I have r squared, an example of a basis would be the set 1, 0, and 0, 1. Because for any vector xy, I can write it as a linear combination. So they span the vector space. Also, if I have some linear combination that's 0, the 0 vector, 0, 0 is this, then I can just like evaluate this vector. And this will turn out to be AB, forcing A to be 0 and B to be 0. So they're linearly independent. And so they're a basis. And so since this basis has 2 elements, this is a 2-dimensional vector space. And so this is what I was telling you about earlier when I told you about how the sort of the geometric meaning and the sort of algebra meaning of dimension line up. Now you see, like, just doing this algebra, I defined the word dimension and said, oh, the dimension of this vector space is 2. And doing geometry, I came to the same conclusion, that the dimension is 2. And so that's why we have this, and so we have this sort of nice property that, oh yeah, the dimension lines up. And so, in fact, you can similarly write down a basis for r to the k and prove it in a very similar way, which is just like the vector that's all zeros except for a 1 in its first component, the vector that's all zeros except for a 1 in its second component, and so on, all the way down to the vector that's all zeros except for a 1 in the last component. And this set has k elements, and it's a basis. You can check without much difficulty. And so this is k-dimensional. So again, the geometry and the algebra line up, and we're happy. So if a vector space, and notice a basis, generally, you don't expect a basis to be unique. There are lots of different bases for a vector space, usually. Obviously, the vector space that's just 0, the only basis is the empty set. But usually you expect there are a whole bunch of different bases, usually. So like, if I wanted r squared, another basis I could have written down is, -1, 2, 3, 97. This will actually be a basis. Though, obviously the proof would be more annoying. But, for example, that's a basis. For a big vector space, you sort of expect most things to be bases. So a basis, when you have the basis, it's generally not unique. You sort of expect like a set with a number of vectors equal to the dimension is sort of quote unquote usually a basis, because like it's usually, again, I'm hand waving, usually they're not linearly dependent. And it turns out like basically another result is that like any linearly independent set. Also, wait, before I get into that, I should say, if the vector space has a finite basis, like what we've been saying, then it's, big shock, finite dimensional. Otherwise, it would be infinite dimensional, and you can define, then the basis would be infinite, and you sort of do more technical things, and I don't want to go there today. So from here on out for today, assume all vector spaces are finite dimensional. Now, infinite dimensional vector spaces are important, but I don't want to talk about them today in this right now. For today, assume any vector space we discuss is finite dimensional. So, okay, given a finite dimensional vector space, we have this result, which again needs proof, and I'm not giving you the proof. Given any linearly independent set of vectors, L, there is some basis B. There is a basis B that has L as a subset. And given any spanning set S, there is a basis B, and or I'll give it a different name. I'll call it beta. That is a subset of S. And these require proof, but I'm not going to give you the proof of that today. And so this sort of gives you this nice result, which is, in this linear algebra book I have over here, and probably in most every, or at least part of it is, and probably in most every introductory linear algebra book, which is that if you have a finite dimensional vector space V of dimension D, and then like if I have a spanning set with D elements, it must be a basis because there's some subset that's a basis. And if it was a proper subset, then it would have fewer than D elements, which contradicts the fact that V has dimension D. So it must be a basis. And conversely, or not conversely, but like if I have a linearly independent set L of D elements, then it's a basis because there's some basis that contains it. And if I had any extra elements, then the basis would be too big. It would have more than D elements, contradicting the fact that V has dimension D. So it would have to be a basis. So now, one special thing about a basis is that if I have a basis, V1 through VD, basis of V, then for any vector V, little v in the vector space V, there is exactly one choice of constants to write V as a linear combination of V1 through VD. The proof of this is not hard, which I'll just quickly outline. Basically, there must be a way of doing it because we said they span V. And if there was more than one way of doing it, if I had two different ways of doing it, then if I subtracted them, I would get the zero vector over here, and I would get some linear combination where the coefficients weren't all zero, contradicting the fact that they're linearly independent. So you get this result. So now, this is about all I want to say about vector spaces per se, because look, these vector spaces, you see that there's, stuff going on. So if one vector space gives you all this interesting stuff, what if we took two vector spaces and sort of connected them? So let's say I have vector spaces V and W. Oh, and by the way, it turns out, as something along the lines of what Brian is saying and what this book says, just as one final side note, it turns out that this 2, 4, 4, 7 turns out to be a basis for R squared, along the lines of what Brian and this book say. And so, as an application, that system of linear equations, as an application, there's a unique way to write 2, 5 as a linear combination of them. And so the system of equations from earlier has a unique solution. There's exactly one solution. Of course, if you just wanted to know that, you could have done it a lot easier by just, doing the method of elimination or the method of substitution or whatever they taught you in school. And I haven't really proved that this is a basis, but it turns out it is. So Of course, to prove it's a basis, you wanted, whatever. But let's move on from that. Of course, I glossed over a lot there. I didn't prove it was a basis. But anyway, let's say I have these vector spaces V and W and then some function f, so that for every vector in V, it assigns some vector in W. But like, I care about the operations on in the vector spaces. I don't just want any old function. Otherwise, like, if I were just going to take any old function, then I might as well just take V and W to just be any old set. So if I wanted to link vector spaces together, if I want to study the properties of vector spaces, I want the function V to sort of respect that there are vector spaces. So I want the function to sort of respect the scalar multiplication and the addition. So I want f of the sum of two vectors to be the sum of the f's of the vectors. This addition is in V, this addition is in W. And then for any number R and any vector V in V, I want f of RV, the scalar multiplication of vectors in V, to be R times f of V, scalar multiplication in W. If these axioms hold, then f is a linear transformation. Now, before I move on, I should say another thing about like the one vector space. We can add vectors, and you can multiply a vector by a number. So you might be sort of eager to say, oh, let's multiply vectors together. We're not going to talk about that today. There is a thing you can do called a dot product, and there is a special type of vector space, an inner product space, which I'll write that down. Inner product space, where you can sort of multiply vectors together. But it's important to note, when you multiply the two vectors and multiply in quotes, you don't get another vector, you get a number. So for example, like, and it turns out to be, we write this sort of multiplication, quote unquote, with a dot, and in the R to the K case, usually we would write it with a dot, and it turns out to be like this, that the dot product of two vectors like this, we call it the dot product because it's sort of like a product, and we write it with a dot, basically. Or I don't know, maybe they called it the dot product and wrote a dot because it was called the dot product, whatever. You can look up the etymology later. It's like the product of each individual pair of components summed up. And I don't plan to say much of anything about this today, but if you do physics again coming up, you will see dot products when, like, in the definition of work, they'll talk about dot products, and these are going to be important. And in particular, dot products can tell you when two vectors are perpendicular. They're perpendicular if their dot product is 0. But again, you can see that in some book or whatever, and maybe the physics lecture will mention that. But I don't plan to say much of anything about that today. So anyway, back to these linear transformations, which was basically a function from V to W satisfying these equations. One other thing I do want to mention about an individual vector space, the 0, there's only one. If you had 2 0 things that you wanted to be 0, called like 0 and like cursive 0, like if you just add them together, since each one is like 0, this 0 plus anything is just the thing. This 0 plus anything, if it really is 0, is just the thing. So they're equal. So there's really only one 0. So I really can't just say the thing that's 0. I really can just say 0 without being ambiguous. But don't worry about that. You probably already understood that anyway. Just didn't explicitly say it. So now, since I've been talking for if you know something about linear algebra, you might have expected me to talk about matrices. And you might be wondering why I've been talking for over an hour and haven't mentioned matrices at all. So I need to tell you about matrices. So basically, let me tell you about matrices. For example, if I want to make a linear transformation from r squared to r squared, basically, so first of all, I should tell you, what is a matrix? Well, formally, a matrix is just an array of numbers. Or a rectangular array of numbers. And so, like, mathematically, this is definitely a true statement. But this is not the highest level way to think about it. There's a sense in which you want to think of a matrix that a matrix is a linear transformation. And I'll show you what I mean by that and how what I'm talking about will even make sense. Because the point is, the point is, a vector is a special type of matrix, just one where one of the dimensions is 1. And so I guess you would, let me make sure I don't switch anything up. Yeah, so yes, I checked in the book, this is definitely correct. So generally, an m by n matrix is just an array of numbers with m rows and n columns. And then each thing is a number. So for example, as an so for example, this is a 2 by 1 matrix, as a sort of silly example. In fact, you could even have a 1 by 1 matrix, for example. And the thing you can do with these matrices, you can add them. And the way you add matrices isn't going to surprise you. Basically, if you have 2 matrices of the same dimension, if I have 2 m by n matrices, then I can add them just by like adding up each component. So, 1, 2, 3, 4, plus 5, 6, 7, 8 is 1 plus 5 gives me 6, 2 plus 6 gives me 8, 3 plus 7 gives me 10, 4 plus 8 gives me 12. So I would get that matrix. Also, in certain scenarios, you can multiply matrices. However, you have to do some fancy footwork. You don't just blithely multiply 2 matrices of the same dimension together. You multiply an m by n matrix with like an n by p matrix, and the outcome is an m by p matrix. And the rule for multiplying them together is some complicated thing. And so you know, if you want to find, this product, 1, 2, 3, 4 times 5, 6, 7, 8, for example, you might hope that it's just going to be 5, 12, 21, 32. No, it's this complicated thing, and it works out to be like 19, 22, 43, 50, I think. But for today, I don't really care that you know how to multiply matrices. If you take a class like these, you'll probably be forced to multiply matrices if your hand is sore, even though Wolfram Alpha can do it easily. And you could, I think anyway, multiplying matrices is an easy job for a computer. What's important, yes, and as Ben says, he'll be teaching the physics class. You should come to that too. It's in a few weeks. But yes. Yeah, so if you have what's important isn't that you be able to do the computations, but that you understand what's going on. So it's this complicated rule, but it will turn out to have a simple interpretation. And that's what's important. So one particularly important case of multiplication is when the second matrix is a column vector, i.e. when P is 1. And in that case, you should understand what's going on. So I will show you an example. For example, if I multiply A, B, C, D by X, Y, the result is AX plus BY times CX plus DY. And then CX plus DY. And basically, and it turns out that this matrix, A, B, C, D, gives a linear transformation. Basically, the linear transformation being map this, the linear transformation applied to this vector, f of this, is this vector. And it turns out that this really is a linear transformation. You can check the axioms and they do work. Yeah. And now, here's the cool part. This might just seem random, but here's the thing. For any linear transformation, there's a matrix that makes it this linear transformation. Because let's say that the linear transformation maps the vector 1, 0 to, for some numbers A and C. I'll write them with capitals, A, C. And let's say that this linear, that it maps this vector to this, the basis. Then I can write anything as any vector x, y. I can write it as a linear combination of these two. So then I can use the linear transformation property to split it up into these two things, into f of this plus f of that. And then I can use the linear transformation property again to pull the constants outside. And then I just know what they are because I wrote them down. And then it turns out that it's this. Which is exactly this for some matrix A, B, C, D. And so basically, it will turn out that these matrices will be in correspondence. You might have to check a little more details, maybe, probably, or yeah. There's a little more detail to check, but basically these matrices, these 2x2 matrices, are in a natural, in sort of a canonical natural way, in one-to-one correspondence with linear transformations from R squared to R squared. Technically, you should check that no two matrices give the same, that you don't have two different matrices giving the same linear transformation. But that's not very hard. Like if you just plug in 1, 0, and 0, 1, you get what you want. And so, you know, basically the linear transformations from R squared to R squared are in one-to-one correspondence with 2x2 matrices, with, I should say, with entries in R, with real entries. And you can basically do exactly the same procedure, which I'll sort of gloss over, but basically you can do exactly the same procedure that linear transformations from R to the N, from R to the M to R to the M are in one-to-one correspondence with M by N matrices. And now you see why we have this weird, and I haven't defined to you exactly how the matrix multiplication works for large matrices, but it works along these lines. And you can basically do the same thing with a little more care and a few more ideas, not much more ideas, but a little more of an idea, and like it works. And you know, these as vector spaces, obviously. And so this tells you what's going on with this weird thing about the product of matrices having these weird dimensions. Because let A be an M by N matrix, and let B be an N by P matrix. So this gives me some map. I'll write them with lowercase letters to basically tell you that they're basically the same thing, but not exactly the same. This gives me some map, lowercase b, a linear transformation from Rp to Rn, and a map A from a linear transformation A from Rn to Rm that these matrices will give you. Now, compose these maps. This will turn out that it has to give you a linear transformation. And so it will give you a function Rp to Rm that's basically like, for any x, map it under B to something B of x, and then map it under A to A of B of x. And then this will give me some map that I'll write as like A circle B to denote the composition. And this is some M by P matrix. And it turns out that this matrix, and this is really important, this matrix corresponds to the product of the matrices A and B. So when they tell you what matrix multiplication is, it basically corresponds to composing linear maps, as Brian said, doing one after the other. And so matrix, if you just saw matrix multiplication and I just wrote down the formula, it doesn't look like a particularly nice formula. And you might just say, what is going on with that formula? It looks so ugly. But it turns out that it has this very nice interpretation as just doing one after the other. And so the matrices gives you the product, like the product of matrices is the composition of the maps. In particular, this tells us that matrix multiplication is associative. If I have 3 matrices, A, B, C, so that the dimensions, line up in a nice way, A times B times C and A times B times C both represent the map that's just like do C first, then B, then A, which is just like a vector X goes to A of B of C of X. And so they're the same. And I haven't exactly told you how you would actually carry out the computation, but you could do it if I told you how. And a computer could do it easily. Okay, it's getting pretty late, so I'm going to wrap up pretty soon. But I want to tell you one more thing, which is that say I have an n by n matrix. And I can, basically, it's a map from Rn to Rn. Now, let me look at this in terms of geometry. Suppose I take, this is a bit annoying to say, like in 2 dimensions, when you have a parallelogram, you get like something like this. In 3 dimensions, you might have something like this, but then like there's another parallelogram, like it might look like this or something. And you could call this like, you could call this like a parallelepiped, or I'm not even totally sure I spelled that right. But like it's a big word. And so, and you can consider its volume. It has a volume, it's some shape, it has some volume. So if I have some vectors, and I want to sort of consider like the signed volume, sort of consider like positive and negative volume. And it's annoying to describe what that, I don't want to go into that, but like you can just sort of imagine for like a 2-dimensional version, like maybe I want this, like if I have sort of a parallelogram that looks like this, or actually, before I get into the intricacies of that, let me just tell you where I'm going with this. But basically, given any parallelepiped in n dimensions with this that these vectors v1 through vn make. So like, an example, if I had a vector A and a vector B, it would make a parallelepiped like this. And a cube is a good example of a parallelepiped in 3 dimensions. Or a hypercube, or whatever, in more dimensions. If I have these vectors that make a parallelepiped, and then I take a linear transformation f, and it gives me these vectors, and then they make some parallelepiped themselves, it turns out that the volume of this parallelepiped is some constant times the volume of this one. I'll call it, V2 and V1. So V2 is some constant times V1. The constant depends only on F. It doesn't depend on which vectors you choose. And I should say the signed volume. And again, like, if I take, if I take this vector first and then this vector, then it, I would consider it positive. But if I did it in the other order and did this one first and then that one, it would be negative as an example. And you can, there's a way of defining positive and negative volumes. Like there's a way of defining what's important is like you take them in a specific order and then you define positive and negative volumes by like stuff. Don't worry about it. But you get positive and negative volumes, whatever. And so the signed volume of this one is a constant times the signed volume of that. And this constant is the determinant of f. And in particular, you can use this to define the determinant of the matrix. And I'm not even totally sure I'm using the word determinant. It seems a bit weird to call it like the determinant of a linear transformation. I'm not even like 100% sure that's correct, but like you can definitely have the determinant of a matrix. And so if you see the determinant for the first time, it's like some weird formula, like it just looks really weird. You have something like if I have a 3x3 matrix, a square matrix. What time is it? I really should forget. Then the determinant works out to just be this big ugly formula. It's like this plus that, like products of entries, plus that, minus that, minus that, minus that. And like, what is that? Why did I just do that? But it turns out that this determinant is exactly the multiplier that the corresponding map multiplies volumes by. So let me erase that in case that's wrong. We're basically like, but I think it should be fine to say the determinant of a linear transformation. But basically that's the point, that the determinant tells you the factor that it multiplies volumes, signed volumes, the factor by which it multiplies the signed volume of a linear transformation, the corresponding linear transformation. And as a corollary, I get that the determinant of the product of matrices is the product of their determinants. Basically, yeah. You can think about that yourself, right? And another thing is, like, if I have a matrix and I multiply it by some vector and get 0, then either the vector is 0, like an n by n matrix and a vector v, then either the vector is 0, and I hope I'm stating this right, I think this should be correct. Either the vector is 0 or the determinant of the matrix is 0. But I think that should be correct. You might want to double check that on Wikipedia or something, but I think that should be correct. And so like this, you can use this to think about the solutions to linear equations, because if this has a non-zero determinant, then it has a bunch of nice things. And you can have the identity matrix, which is like all ones on the diagonal and zeros off it. So like the 3x3 identity matrix looks like this. And this matrix times anything is just the same matrix. And you can have the inverse of a matrix whose determinant is not 0, basically, if it's a square matrix, et cetera, and lots of nice things. And so, and you can even have linear algebra over you can even have linear algebra over like other number systems. You could do it over the complex numbers or the rational numbers, or even like the integers modulo a prime. And you could have these vector spaces, though, it might be a bit weird to think of volumes modulo a prime number or something. So don't think about that too much, but mostly most of this stuff just all works out. And there's a lot more stuff. You can look up, you know, eigenvalues and eigenvectors. I'll write those down. And, you know, eigenvalues, eigenvectors. And there's a nice theorem called the Cayley-Hamilton theorem that you can look up later. Characteristic polynomial of a matrix. There are lots of things. There are lots of things you can study. So, you know, you can just look up stuff on Wikipedia. Also, for a further reference, you can, if you look up the book which he has on his website by Evan Chen, the quite large book, An Infinitely Large Napkin is the name of the book. And so he has it on his website, so you can read it for free without, you can read it for free legally. So that's fun. And so you can read lots of cool stuff, and there's lots of cool stuff in that book. But, you know, if you read too much of that book, you'll see spoilers for future seminars. Ha 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 ha. But, you know, anyway, so that's, I guess, all I'm going to say for today. I've already kept you for like, you know, like almost 2 hours. So I guess I'll end the meeting. If you have any further questions, you can, I guess, email us at, I think our email address is mathdivulged@gmail.com. Anyway, you can find that for sure on our website, which is just mathdivulged.com. And so, okay, I guess that'll wrap up for today. So thank you all so much for coming. Thank you to everyone